I just started this YouTube channel on fractals and fractal art, so I figured it'd be a good idea to have a video describing just what a fractal is. It's motivated in part actually by a post someone put on one of my groups in Facebook. Now Facebook doesn't make it easy to find stuff you've already seen, so I can't find it anymore. But they ask a seemingly innocuous question. Is a spiral a fractal? A lot of people answered enthusiastically, yes, of course a spiral is a fractal. One person even explained their reasoning. If you zoom into a spiral, you see a spiral. Therefore, a spiral must be a fractal. Of course, by that reasoning, if you zoom into a line, you get a line, so a line must be a fractal too. And of course, if you zoom into a spiral other than the center, you don't get a spiral, you get a curved line. Let's explore this a bit. I'm using one of my favorite fractal programs, JWildfire, which I programmed to make a spiral. If we zoom into the spiral looks the same. If we zoom even more, JWildfire has actually two zoom controls here, the spiral still looks the same. Mathematically, it's exactly the same. The minor differences shown here are artifacts of the software. And we can do the same thing with a line. So here's a line. If we zoom into it, it's still a line. But let's go back to the spiral and reset the view. And let's zoom into somewhere else. To do that, I'm going to turn the guides on for a minute so that I can go and move one of the spiral lines into view there. Now if we zoom, we see a bunch of lines now, and if we zoom even more, we see just a single curved line. It doesn't look much like a spiral. Compare this to a well-known fractal, the Koch curve. We'll see how to make a Koch curve in a minute, but for now, let's just move again some point on the curve to the center and zoom in. So we zoom in, it still looks pretty much like a Koch curve. If we zoom in still further, it still looks like a Koch curve. I didn't get it exactly on a horizontal thing, so now it's vertical, but still, it looks just like a Koch curve. Let's reset and try a different point. Let's say the end point right here. Okay, if we zoom in, it looks exactly the same. In fact, it is exactly the same. Zoom in even more. Well, I didn't get exactly right on the thing, but you can see that it's still exactly the same when we zoom in. So is a spiral a fractal? Well, let's come back to that after we look at the definition of a fractal. There's really not a single definition that everyone agrees on, but there's a lot of characteristics that most people agree the fractal should have. The first one is self-similarity. That's the one we just looked at. In fact, the Koch curve is a wonderful example of this. As you zoom into the Koch curve, it looks the same, no matter what scale you're at. If we look at how a Koch curve is made, we'll see why it has this property. We start with a line segment, which we divide into three sections. We remove the middle section and replace it with two segments of the same length at a 60-degree angle. Now we have four connected line segments. We repeat the process for each one of them, dividing each into three segments and replacing the middle one. This makes 16 segments, and we do this again and again. Since each segment, no matter how small, gets the same treatment, the Koch curve will look exactly the same at any zoom level. Self-similarity isn't always exact. For example, let's zoom into the famous Mandelbrot set. We'll use a program called Chaos, which is designed for real-time zooming. The Mandelbrot set has an iconic shape. It has this main cardioid, a heart-shaped thing, and it's surrounded by smaller bulbs, which are in turn surrounded by even smaller bulbs. And this goes on forever. To zoom in chaos, we put the cursor where we want to zoom and just press and hold the button to zoom. So we can see we zoomed a little bit, and the Mandelbrot set is full of smaller copies of itself. These are sometimes called mini-brots or midgets, but there's infinitely many of them, and they're fun to find. There are also points called Mashirevich points. That's just like this is one of them here. If we click in one of these and zoom in, we'll zoom in forever, and it just basically looks exactly the same as we go in. There's lots of Mashirevich points. In fact, infinitely many Mashirevich points. They all look a little different, but there's the same property. You can zoom in. The Mandelbrot set is infinitely interesting and beautiful, and you can spend a lot of time having fun zooming into it. But let's go on. Another common characteristic of fractals, in fact the one that Ben Mandelbrot used when he was working with fractals, is that the fractal dimension is strictly greater than the topological dimension. Now, the mathematics of dimension is surprisingly complex. In fact, the term fractal dimension can refer to one of about a dozen different kinds of dimension. We won't get too deep into the math here. In fact, any mathematicians that are watching may want to skip ahead a few minutes just so you don't cringe during my explanations. As fractal artists, we rarely need to worry about dimension. But as we learn about fractals, the term comes up quite a bit, so let's get an intuitive feel for what it means. Topological dimension is something we're all familiar with. A point has 0 dimensions, a line has 1 dimension, a surface has 2 dimensions, a solid has 3 dimensions. And this is true even if the object is embedded in a higher dimension space. For example, a point that's in 3-dimensional space has an x, y, and z coordinate, but the point itself is still 0 dimension. A line might be bent into a circle or a spiral or a Koch curve, but the line still has dimension 1. The surface of a sphere has dimension 2, even though the object, the solid that it's surrounding, has a dimension 3. Mathematicians, of course, can't rely on the intuition like this. We need something more formal to try to understand exactly what a dimension is. The general approach is to try to cover the object with balls. Now, we're going to be working with 2 dimensions for our examples, just a lot easier that way. So the balls are actually going to be 2-dimensional disks or filled in circles. Let's start with a circle. So here's a circle, and we can cover it with balls, or in our case, again, disks, however we want. For every point in the object that we're covering, the circle, the balls will overlap, so some points will be in more than one ball. We need to try to minimize that overlap as much as we can, so that points are in as few balls as possible. To do this, we shrink the balls, like this. If we can cover the object with no overlap at all, the object has dimension 0. We can't do that here. There's no way to avoid covering some of the points with 2 balls. But we can cover it so that no points are in 3 balls. 2 is the maximum that we actually need. So this object has dimension 1. Let's look at an object with dimension 2, a disk. When we cover it with balls, some points will be in a single ball, some points will be in 2 balls, but there's no way to avoid covering a few points with 3 balls, like these in the middle here. This means the object has dimension 2. If we're in 3-dimensional space, we'd work with 3-dimensional balls, which are filled in spheres, and any covering of a solid object would require some points of the solid to be covered by 4 balls, meaning the object has dimension 3. The topological dimension is 1 less than the largest number of balls of the points that the points are in. So what about a Koch curve? We follow the same procedure. We cover it with balls. In this case, some points are in 2 balls, but none are in 3, so the topological dimension is 1. Now, fractal dimension is an interesting concept. It's a measure of how the detail in the object changes with scale. Remember, when we zoomed into it, we found that it looks the same as we zoom into it. That's what fractal is all about. Unlike topological dimension, which is always a natural number, fractal dimensions can be fractional. So we approach it mathematically the same way we did topologically, by covering the object with balls. But this time, instead of looking for overlaps, we compare how many balls it takes to cover an object at various scales. So let's go back to our circle and cover it with balls. And again, we try to avoid overlap as much as possible. In this case, the circle is nicely covered with 9 balls of size 2.5. Now, the units of the size are arbitrary. In this case, it just happens to be the ones that I used in LibreOffice Draw. But what we do now is we reduce the size of the balls and see how it changes. We now have 18 balls of size 1.25. So we half the size of the ball and we double the number of balls, which seems logical. To actually find the dimension, we use this formula here. We take the log of the new number of balls divided by the old number of balls, and we divide that by the log of the new size divided by the old size. And the answer we get is 1. Now, log is a very useful mathematical tool. It means logarithm. If you're not familiar with how it works, we're not going to get into it here. Just think of it as a button on your calculator. Anyway, let's try the same thing with the disk. So here's a disk, and we cover it with 9 balls, slightly larger than before, just so they'd fit it in 9 balls easily. And again, we compare this with covering it with smaller balls. We divide the size of the disk in half to 1.45. Now it takes 36 balls, 4 times as many balls to cover the disk. Now this makes sense because we have to double both dimensions, both the XY dimension and the horizontal dimension and the vertical dimension. And 2 times 2 is 4. But again, plugging in the numbers here, we get that the disk here has fractal dimension 2. Again, the same as the topological dimension. Now, using the characteristic that started this whole investigation into dimension, the fractal dimension is not greater than the topological dimension. It's the same. So neither the disk nor the circle is a fractal. And it's kind of encouraging that the fractal dimension matches the topological dimension for non-fractals. But let's see what happens when we apply this to a fractal, like a Koch curve. So here the Koch curve is covered with 9 balls, size 2.6. Now remember those numbers, we'll come back to them. When we half the size of the balls, now we need 21 of them, more than the 18 we needed before, to cover the curve. When we do the calculation, we get an interesting result. The dimension is now 1.22. That's actually a bit low. We can improve our accuracy by making the balls even smaller. So here, half the size again. We now need 52 balls to cover the Koch curve of size 0.65, and plugging in those numbers, again 52, the current number, divided by 9, the original number, and the current size 0.65 divided by the original size 0.26, and we get about 1.265. That's actually pretty close. The actual value is 1.26186, so we're a little bit high. We can get more accurate measurements if we make the balls smaller and smaller. Okay, enough math for this video. None of this was actually mathematically rigorous, but hopefully you have an idea of the approach that mathematicians sometimes use when they approach the subject of dimension. We don't usually have to worry about dimension when we're making fractal art, but scholars have used these techniques to analyze other art pieces. This is an image of Jackson Pollock's painting Convergence. This small reproduction doesn't do justice to the real thing, which is nearly 8 feet tall and 13 feet wide and has wonderful textures from the layers of paint he used to make it. He created it in 1952. He didn't use a computer. He didn't know anything about fractals. Yet this and his other paintings have fractal dimensions between 1.3 and 1.5. And this might help explain the powerful aesthetics of his work. The last characteristic of fractals that we'll cover here is a little bit strange in that it's not based on the fractal itself, but on how the fractal is defined. Specifically, fractals have an iterative or a recursive definition. Iterative just means it's repeated over and over again. Recursive means it's defined in terms of itself. And we saw an example of this with the Koch curve. When we look at the definition of a Koch curve, for each new segment, we apply that definition again for every segment we just created to get more segments. That's recursion. In fact, when the subject of recursion is taught in computer programming classes, it's a common exercise to write a program to draw a Koch curve. Now, we used a geometric definition to define the Koch curve, but there's lots of other ways to define fractals. In fact, there's several other ways to define a Koch curve. The most common method used in fractal art programs is based on orbits. I guess we'll need a little bit more math. We start by defining a mapping from points to points. So it takes a point and maps it to another point. For example, the Mandelbrot set uses a fairly simple mapping. Z maps to z squared plus c. But basically we start with a point, and we run the mapping, we get a second point. And we put that point to the mapping, we get a third point. And we do it again, we get a fourth point, and so on and so forth. The set of points we get by iterating the mapping over and over again on the starting point is called the orbit of that point under that mapping. To better understand this concept, let's use a standard calculator to show some trivial, although boring, orbits. The points we'll be using are one-dimensional. They're points on the number line. And the mapping will start with this square root, which is this button on the calculator. Let's pick the point 5 to start, and push square root, and we get the square root of the new point, 2.236. That's our first orbit point. Press square root again, we get 1.495. That's our second orbit point. We repeat and get 1.223, and we just keep going, and we can do it as much as we want. Notice that the numbers keep getting closer and closer to 1. 1 is a special point. If we start with 1, press square root, it stays 1. And of course, since it's there, we push it all we want, it'll always be 1. That's a trivial orbit, just the point 1. It's what we call an attractor of the mapping because it attracts points, as we just saw. Let's start with a different point, like point 5. Its orbit is 0.707, 0.841, 0.917, and so forth. As the more we go, the closer it gets to 1. Now let's look at the opposite mapping, the square. That's the button right next to it. Again, if we start with 1, it just stays there. 1 squared is always 1. Let's start with just a little teeny bit higher than 1, 1.01. That's just 1/100th higher than 1. Square it, we get something a little bit bigger, 1 2/100ths, 1.04, and so forth. After just 10 iterations, it's over 26,000. Similarly, let's start at a point just less than 1, 0.99. Again, 1/100th less than 1. If we square that, it gets further and further away from 1 the more we go, getting smaller and smaller. So for this mapping, 1 is not an attractor, we call it a repeller, since it pushes points away from itself. To make fractal art, we use a lot more interesting mappings than a simple square root or square. This is the attractor of a map attributed to Peter de Jong. It's a lot more interesting than a single point. The formula is shown down at the bottom left there. Don't worry too much about what it means, but do notice that it has parameters A, B, C, and D. The particular values for this image are shown. Most fractal art programs provide a way for users to change parameters like this, which can produce very different results. This shows one way to use a mapping to produce a fractal image. If the mapping has an attractor like this one does, we start with some random points and compute their orbits. The mapping will pull the orbit towards the attractor. You project each orbit point to the corresponding image pixel and color it somehow. Here we use a single color. Pixels corresponding to lots of orbit points are brighter than those corresponding to fewer, producing a density map of the attractor. Mappings can also combine multiple submappings. This image is made with 4 affine mappings, which shrink the input point, that is, move it towards the origin. They rotate the point around the origin and they move it to produce a new point. The math term for this kind of mapping is iterative function system, or IFS, and it'll be an attractor as long as certain conditions are met. We don't need to worry about those conditions when we're interacting with fractal software, because if we do something and the fractal disappears, we're not meeting the conditions, we just back up and try something else. Iterated function systems are the basis of flame fractals used by programs like JWildFire, which is I used here. Some others are Apophysis, Chaotica, and Factorium. Coloring is based on the particular sequence of submappings that reached a particular point. When the mapping is a repeller, as is the case with the Mandelbrot fractal, a different method is required to render it to an image. This image uses a method known as escape time. For each pixel in the image, we pick a representative point and start computing its orbit. If the orbit is outside the fractal, the mapping will repel it, and it'll get further and further away from the origin. When it reaches some threshold, like 1,000 is used here, we say that it escapes, so we know it's outside. The closer the point is to the fractal, the longer it will take to escape. The number of iterations it took to escape is the escape time, which is what we use to select a color. Points inside the fractal won't escape, so after some maximum number of iterations, we'll give up and just color it black. This method of rendering fractals is especially amenable to deep zooms, unlike plotting orbit points, where a zoom will just mean most of the points are ignored since they are outside the image. With escape time, we only look at points that are actually in the image. This image is magnified about 65 million times, which frankly isn't very deep at all. But using escape time to color a fractal only works well in 2 dimensions. For 3-dimensional fractals like this Mandel bulb, a different approach is used. We still use escape time, but now we use it to estimate the distance from a point to the fractal. Basically, we shoot away from each pixel of the image towards the fractal. There's not an easy way to tell where it intersects the fractal, or even if it does intersect it. So we need to move along the points of the ray until we reach the fractal. The distance estimate tells us how far we can move before checking again. And again, the distance estimate came from the escape time of the iterating the mapping. The details are kind of complex, but this can create stunning images of 3-dimensional fractals. Let's look at one more method to create images from a repeller mapping called orbit traps. This is a Julia fractal, closely related to the Mandelbrot fractal. The one on the left was rendered using the escape time method. The one on the right was rendered using orbit traps. Like escape time, we pick a point for each pixel in the image and compute its orbit. But now we compare each orbit point with a shape called a trap. Orbit points that lie inside the trap are, well, trapped, and they're used to determine the color of the pixel. There are a lot of different options. Here the trap is shaped like an X. If there's more than one point in the trap that gets trapped, the one closest to the trap's center is used. Then the distance of that point from the center is used to select the color. The result usually has lots of copies of the trap shape fractally distributed through the image, as we see here. So let's go back to our question. Is a spiral a fractal? Technically, no. It's only self-similar in the very center. The fractal dimension is 1, which is the same as the topological dimension. And while different spirals have different mathematical definitions, none of them involve iteration or recursion. But does it really matter? Fractal geometry provides methods for describing and analyzing complex systems that are intractable by no other means. But that doesn't mean we can't use them for simpler things like spirals and circles. It's just that the other ways are easier. More to the point, for fractal artists, fractal programs are more than capable of generating images that are technically not fractals. Does that mean we can't call them fractals? Well, I don't think so. I call them fractals. Let's have a look at one final example. This is the fractal program J Wildfire again. I've used the Julian variation to create a circle. By making small adjustments, we'll get the well-known fractals called Julia sets. And we've seen a couple of these already. They're closely related to the Mandelbrot set we zoomed into earlier. The circle is a special case, which descriptions of the Julia set state is not a fractal. But is that really true? Let's add some color. We now color it by the distance the point travels as it goes along the circle. And it certainly looks fractal now. The colors come from a gradient containing lots of narrow stripes. Notice how the stripes on the circle are far apart on the left, but get closer and closer as they go to the right. We're limited here by the gradient's finite structure, but this gives a hint of the fractal structure of this circle. The fractal structure of this supposed non-fractal is even more apparent when we use orbit traps. Here is the same fractal in a different program, ultrafractal, and it's colored using an orbit trap that's a circle centered at the origin. We can see the trap better if we change the Julia seed to something besides 0. Now we can see the fractally distributed circles that's typical of orbit traps. But there's no fractal structure apparent when the Julia seed is 0, just a circle. But watch what happens when we move the trap. Now there's a nice fractal structure. If we zoom into this a little bit, we can see that that structure persists at different scales. So here's my conclusion. Fractal geometry provides useful tools for analyzing complex systems and for producing unique and beautiful pieces of art. But don't worry about whether something's a fractal or not. It doesn't usually matter.